Good morning, Lola. How are you? I don't hear anything. Please test your microphone.
Morning, Dr. Kivin.
Oh, okay, good morning, Lola. Yeah. Nice hearing you. Hello, Hadassah. Nice seeing you connected. As we have a minute before, I'm making you co-hosts. So if you see anyone joining, please try to compete with me and admit them to the meeting earlier. Yeah, thank you. How your projects are doing?
I'm slowly putting stuff together.
Okay, yeah, that's great. So just use the philosophy of submitting jobs ahead and let them to sit in a queue, just planning a few steps before.
Oh, I did have a question on submitting jobs.
Huh?
So I remember you in class saying like we can either submit it as a debug or as regular. At what
Yes.
when would you recommend doing regular versus just debug jobs? I forgot.
So, regular is if you need more than 30 minutes. So 30 minutes is pathetic. You cannot do anything, only small test jobs. And if you need like long optimization or molecular dynamics, then definitely you need regular. So there are two ways to get more numerical resources. One is to request more. Nodes and CPUs, and another one is to request more time. And basically one should use both. When if the model is really small, one can optimize something or do quick molecular dynamics in a debug queue. But if you are in the productive stage of doing something serious, one should plan on going to regular and submit jobs that last for like 24 hours or 48 hours. So it's very justified. Hello, Hanmant. Nice seeing you connected.
Good morning, Dr. Kivin.
Okay, I think you all are co-hosts. I will go ahead with lecture materials, and first maybe 10-15 minutes it will be a repetition of what we did yesterday, because there is the schedules do not coincide. So Lola will see something for the second time, and Hanmant and Hadassah will see things for the first time. And if you see anyone joining, please go ahead and admit. Okay, so we are in the computational chemistry class looking on predicting observables that can be computed to experiments, so computational material science. And in order to achieve this goal, we get some background theories and learn how to process models in the right pieces of software. And we are starting new chapter of excited states and spectra in the as a main activity for lectures, but outside of the lectures we are completing the projects. So many thanks to those who selected projects. It will be main contribution to the grade, and if you are volunteering, please consider joining and doing it at the same time. So projects can be approximately say categorized on several directions. So there are few projects that focus on adsorption of small molecules on surfaces. There are projects focusing on the charge transfer. There are several projects looking for optical properties of metal organic complexes. There are a couple of projects dealing with transition states analysis and optimizing infrared emission of carbon nanotubes, and there are a couple of projects for charged particles passing through the solid electrolyte. So there is no how to say protocol. There are no prescriptions for research. It's very creative process, but some common motifs can be suggested. So if you already know what to do, if you have your own plan, please follow your own plan. I'm giving suggestions just so that you feel some backup ideas. And before we go forward, I want to add something that I wasn't telling yesterday. The nature of the social part of scientific research includes communication with peers. So it includes reviewing of your reviewing of your papers by editors and reviewers, and it includes open presentations on the conferences where whatever you generate, your results can be eventually criticized. So one motivation for research is curiosity and internal wish to just do high quality research. But there is a second portion just to avoid criticism and be well received. So of course, the first is more important, but second, by nature of our science, no one is a abstract scientist in a vacuum. Everyone works in the environment of other researchers, and one needs to take into account their possible feedback. So if you are if you're generating any of the results that we were discussing, and we will discuss in the future, the numerical values of observables do depend on methodology. So if as you already know, there are several methods for electronic structure, like at least Hartree-Fock and DFT, and we will get through more of the methods. But even if you narrow down your methodology only to DFT, there are several exchange correlation functionals that we briefly overviewed yesterday, right? If you are running your jobs in Gaussian, you just practice the drop-down menu and select which functional you prefer. If you are running jobs in VASP, there are templates of the in-car file that are oriented to include to do calculations with certain exchange correlation functional and sometimes hybrid. So there is a very healthy approach, which I do not demand here in the course, but just a second. Yes, I do not demand the following thing, but it is very reasonable to have if you foresee other researchers watching what you're doing, and there will be guest visitors on the final presentation that typically asking the following question: how reliable, how repeatable, how much your results are agreeing with experiment, and how do they depend on the choice of exchange correlation functional. So what are we going to do? What I'm going to instruct in the rest of the lectures and labs is based on only one functional, GGA functional Perdue-Burg-Erzhenhof PBE, but this functional is ideal in a sense of calculations run quick, but it is not ideal in the aspect of predicting the best HOMO-LUMO gap energies and other numerical values of observables. So if you plan to convert your in-class project into true solid research in the future, or if you want to disarm your potential criticizers during your public talk, you may consider to select an observable such as the energy offset between HOMO and LUMA, and for a single point without geometry optimization, and redo it with few functionals. So it is one of the possible additions to your research procedure, and it is very much appreciated by community. Hello, Amir. Hello, Umar. Nice seeing you connected. Okay, so I'm not sure if I will ever repeat the idea about redoing some research with exchange different functionals, but please make a note and consider doing it especially if you want to continue this sort of research activity beyond the class. Okay, so let me continue repeating things from yesterday. So a very simple and common arrangement of computational research is a concept of heterogeneous interface. So the question is quite, I would say, philosophical. Hello, Adam. Nice seeing you connected. So if you do have two systems like A and B, which can be very different in your for each project, and the question is whether property of model A and property of model B are additive. Are they stay the same after we bring these components together? So as those of you who have chemical background know that it's often not so, because components may come into reaction and dramatically change their properties, right? Adam, would you agree? Okay, yeah, thank you for confirming. One can check this concept just, it's basically philosophical background of many ways of research, not only computational chemistry, like whether signatures or properties of two objects stay the same if one brings together, whether the summation of property of A and property of B is equal to property of A plus B. And the simplest way to check this philosophical concept is to check the total energy of the combined object. So total energy of the hybrid minus total energy of A and total energy of B. So if it is 0, it means they do not interact. Like if you take like atom of helium and atom of neon, put them together, they do not, their interaction is vanishing and you will be very close to 0. But for most systems that are placed close together, there will be some non-zero. If this is called binding energy, if it is negative, it means they attract each other, they like to be together. If it is positive, it means they repel each other. And the binding energy can be explored on experiment. The rate of reaction, often dependence of rate of reaction on a temperature, typically depends on the binding energy in several experiments. But I'm not going to review, but it is standard experimental measurement to find the value of binding energy. And it is the simplest calculation that all of us can do. if you can separate your object on two components. Continuing this idea, one can look for density of states of the hybrid system, density of states of system A, density of states of system B, and look on these three lines together, whether density of states of a hybrid system is equal, can be represented as a superposition of A and B, or when models are brought together, they mutually affect each other, and it is not just overlaying two density of states, but they shift and change intensities. So also some basic and quite relevant thing. And of course, one can look for other observables like absorption spectra, whether absorption spectra of the components are equal to, can be added together, or they create new features. If there, an example, if there is a charge transfer of either electron and hole between A and B, then absorption spectrum of a hybrid will be not equal to spectrum of object A and object B. Okay, so this is the simplest approach to computational research. Another motif, and again, let me repeat since a couple of attendees joined a little later, there are no flow charts and prescriptions for research. Research is a very creative activity, and what I'm suggesting is quite optional. If you may have much better plans on your own. So a response of a model to temperature. So one selects a model, optimizes geometry, and finds observables. Then on the parallel shoulder, one sets it on a thermostat by assigning momentum, then runs molecular dynamics, and then during the molecular dynamics trajectory or at the end of molecular dynamics trajectory, one looks for same observables, and then one compares the observables before and after, and makes like intellectual analysis of how this comparison help us to learn something more about the system. So if we are describing solid, stable objects, the change can be minimal. But one of the examples when this change will be dramatic is when heat induces reaction, or heat induces desorption of pieces of model from each other. If you made a combined model, if you put a molecule on the top of a substrate, then by heating it can depart. It can be desorbed. So it is something that many of us can observe. In previous years, there were several projects on combustion when one just mixes fuel and oxidizers like hydrogen and fluorine, or oxygen and methane, just heats it up and runs molecular dynamics and observes how the products of the combustion are getting created. So the thermalization may lead to dramatical changes into both chemical composition, structure, and electronic properties. And there is another aspect that we do not have time to complete in a couple of weeks, but some of you may decide to follow in the future. Lola already is doing it. So upon thermalization, the orthogonality of electronic states is broken because ions are moving, they are departing from optimal geometry, and motion of nuclei induce transitions between electronic states. So it refers us back to the very beginning of the class when we considered Born-Oppenheimer approximation. So molecular dynamics is a way to go beyond Born-Oppenheimer. Molecular dynamics is gives opportunity to break the disconnected status of electronic and nuclear degrees of freedom and induced transitions. So the molecular dynamics may allow so-called non-adiabatic transitions between electronic states. And this is quite interesting and very competitive area of research that can be added to most of the research projects that we are doing. But I just want to be fair, it is not possible in 2 weeks. This calculation would take like at least 3 months in the most optimal arrangement. Okay. So again, it's not requirement, it's only a possible suggestion. So one can make multiple runs for like either ground state or during thermalization, look for different observables like density of states, spectra, and so plotting orbitals. And these observables can be repeated for different electronic configurations. So it is another dimensionality of the research. So one can build tables like this, do calculations for different configurations, and see how change of electronic configuration, namely charge, multiplicity, and excitation by Fermi weight, affects density of states, spectra, and other things. I think it is what, do we have excited? Yes, neutral spinless excited. It is what Adam is planning to do, right? To my understanding. So I believe it is enough input for going forward with the research projects, and just to have all of us as a team organized, let me announce the assignment. So please consider to complete as much of your calculations as possible in 2 weeks and 1 day by lab on Wednesday, April 27th, and bring not to the class, but to the lab 3 printed copies of figures and tables summarizing your research activity. I plan to ask you to do few more sections, like describe these figures and tables by text, but it is secondary. Just plan on having this major parts of your report ready in 2 weeks. Why I'm asking to do it by not by the class, but by the lab time. This semester, everyone is so busy and schedules are not overlapping, and the lab is only time when we all can see each other in person. So on that Wednesday, it will be one of the 2 most important meetings. We will practice the internal review. We will make a mock game of journal editors. So we will provide feedback to each other on this work, and it will help to improve the reports towards final grading. But it is very time sensitive. If you think it is not possible to complete this part by this date, talk to me immediately, or because it is most critical part of the class. Later on, there will be presentations, but it's basically why we meet and what is the main goal of the class. And I'm not insisting on literally following this numbering and titles of figures. I admit creativity. So 7 figures, it's mostly guiding. Please do not do more than 7. If you do less, it is okay. So more than 7 figures is not possible to grade. But of course, you can do multiple lines per panel, and you can do multiple panels per figure. So maybe in one of the future in-class meetings, I will show demonstrations of the reports in the same class in previous years. So like the logic, the possible logic is that one describes the geometry, reports either energies or homoluma gap or energy binding in a table, or then comparing density of states for different electronic configurations, pairs of orbitals. And if you decide to do thermal analysis to heat and run molecular dynamics, one can show snapshots of molecular dynamics, show how total energy changes over time. And then back from here, one can show like density of states and spectra before and after molecular dynamics. So it will be more than ideal, more than perfect for this class. Okay, no, it's some different number. Okay, 21 and 24. Let me, before we go to academic part, let me check if there are any questions on this research projects. Just please vote by thumb up if you are, if it looks reasonable, or thumb down if it is unreasonable. Wave a hand if not sure. Okay, thank you for supporting. Adam, do not hesitate if there are questions or if you want to protest. Okay. Yeah, thank you. So going forward with lecture material. Here is the last slide before you have presented a manual on the WASP software. So it is two mutually enclosed loops that most of the software pieces do when we do either molecular dynamics or geometry optimization. So there is one starts with the geometry, and then one makes a loop for improving positions of ions for geometry. So incrementing, finding gradient, even finding increment of positions. But in order to be able to do so, one uses this internal block where one runs another cycle, self-consistent cycle, for finding total energies through Kohn-Sham procedure, right? Like density, potential, one electron Kohn-Sham equations for one electron Kohn-Sham orbitals. And then one constructs density by adding together absolute value squared of all occupied Kohn-Sham orbitals. And then the energy is computed as functional of the density, old and new. And if it converges, then we use total energy to compute gradient and improve geometry. So I would like to reattract your attention, to focus your attention onto the equation for density. So density is composed as adding together distribution absolute value squared of all Kohn-Sham orbitals. We are going to use this equation today, and we are going to modify it. Here are some words about excited states, and before the meeting, I believe I did share some online materials on this subject. So the experimental part of natural sciences typically deals with looking for a response of a model of an object, of a sample to a stimulus. And most typical stimulus is electromagnetic radiation, but it can be also heat, mechanical, just injection of electrons. And upon stimulus, it is very, very frequent that sample model is converted from ground to excited state. So we do need tools that allow to describe excited states, and those tools are different from anything we did before. There are connections, but basically one just starts over. It's like a new course. Okay, but I will try to be as close as possible to what we already did. So there will be a couple of ugly slides that I didn't update it through the years, but I'm inviting you to forgive their poor graphical shape and focus on their content. So probably I will need to make little votes to make sure that we all are on the same page. So Konsham. Let me ask if everyone admits, that the top line of the slide is the same as we did in the Konsham algorithm. So it is just a protocol to create density if you do know the Konsham orbitals. Please vote with thumb up if you agree, or thumb down, or something other if you disagree. Thank you, Hadassah. Thank you, Mark. Thank you, Hanman. Thank you, Adam. Umar, Amir, and Lola, please vote if you agree or express concern if you disagree. Okay, thank you. Amir, are you happy with the first line on this slide? Okay, yeah, thank you. So now I'm slowly going away from it, but it will be very infinitesimal steps. So as a next step, I want to replace this upper limit where we make summation over the highest occupied to infinity, or to as many orbitals as are available in our calculation. But I want these two equations to be equivalent. So for this purpose, I put a weight factor, a factor F, and the rest of the equation is the same. So it's Konsham orbital, Konsham orbital. So in order these equations to be equal, we design this factor to be 1 if orbital is below or equal to HOMO, and 0 if it is above HOMO. Let's make a little vote on this little equation. So would you approve that first and second lines are the same? Yeah, thank you, Hanman. Thank you, Hadassah. Thank you, Amir. Thank you, Adam. Thank you, Umar. Thank you, Amara. Well, are there any concerns, or you approve this equation? Okay, yeah, thank you. Okay, now let's do a little motivation in the next step. So we are approaching the presentation by Adam a week ago, where he taught us how to modify this distribution function. So this F function is what we set up by Fermi weight, Fer-V. Let me write it down. Fer-V. So by default, it is 1, 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0. But we do have an option to put 0 in one of the originally occupied orbitals and put 1 in one of the originally empty orbitals. And then there is a specific code for making it in the VASP input. So in the very lowest possible approximation, we can describe excited states by repopulating orbitals and then plugging in modified density into standard DFT procedure. This is a very strong approximation. It is not the standard in the community. We just admit it as something that one can get with minimal numerical expense. Okay. And now I'm going to introduce and describe one more equation, which is an expansion of 2 previous equations. And after introducing this equation, I would like to make another set of votes on it. So once again, we do have 2 Kohn-Sham equations, one with star conjugated, another without star. So it is a similarity. Before, we used to have the same indices, I. Now we do have different indices, I and j. If you do have 2 indices, lowercase I, lowercase j. If you have 2 indices, just to be mathematically correct, we need to do 2 summations. One summation over I, another summation over j. And if our before we had a factor that did depend on 1 index, I. Now we have 2 indices, I and j. So we also have a factor. And just to follow the notation in community, we can call it rho. Some people call it lowercase n. So in order to make this equation absolutely equivalent to 2 previous equations, we may set a specific conditions, specific requirements for this factor. We may request that it will be 0 if 2 indices are not equal to each other. So if indices are not equal to each other, it will be 0. So it will automatically cancel summation and all complications. And in addition, we can say that it will be 1 only if indices are equal and if they are smaller or equal than HOMO, which means this factor will be 1, 1 up to HOMO, then 0, 0, and the rest of elements will be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So I'm going to bring up the panel with faces and ask, would you approve this equation, that this equation is equivalent to 2 previous ones, that it is a reasonable, mathematically correct representation of the density in terms of Kohn-Sham orbitals? So please vote. Thank you, Hadassah. Thank you, Hanman. Thank you, Omar. Thank you, Umar. Thank you, Adam. Thank you, Amir. Lola, thank you for approving. Okay, yeah, many thanks. I'm very happy for your approval of this equation. Now let's give them names. Basically, it's only one name. The object on the left is density, and it is continuous. And orbitals, because density is defined as a Cartesian position space, the orbitals are also continuous. They depend on positions in space. Is like when we plot orbitals in VMD or in Gauss view. But connection between orbitals and density comes through this discrete matrix. So this matrix help us to compose density out of orbitals. So this matrix helps to generate density. So it is quite reasonable to call it density matrix. I hope everyone approves it. Okay, let's try going a little bit more forward. So in I can skip this slide. The distribution in equation number 2, if you number them, let me go back and call like this one was equation 1. Here is equation 2. And this one is equation 3. So in equation 2, the function f can be continuous, and it is the typically is taken as a Fermi-Dirac distribution, and what you see in ground state DFT. If you look into states, into list of orbitals, you may see that there are fractional orbitals where HOMO has population a little less than 2 and LUMO has population a little more than 0, right? You did observe it. By the way, if you are using our local codes for oscillator strengths, you may manually bring the population of all occupied orbitals to discrete values and all unoccupied values to also discrete values. It will make the oscillator strengths code work more healthy and avoid some errors. Just a little hint. Okay, so this continuous distribution of occupations is coming from Fermi-Dirac equation, which is here, and it is computed based on this Boltzmann factor, energy of orbital, and temperature. Okay. Now I'm going to analyze equation 3 and maybe let's call it equation 4. So I'm going to introduce it and then maybe vote if everyone is happy with it. So here I'm trying to rewrite equation 3. The only difference from what we did on previous slides and what is here, that instead of running the indices from 1 to infinity, I'm replacing each summation onto 2 segments, running an index from 1 to HOMO and then from LUMO to infinity. So like I goes from 1 to HOMO and then from LUMO to infinity. And same for J, right? So then if I practice this trick in respect to both I and J indices, then the equation 3, where we had 2 summations and just 1 line, 1 term. Now we chop the equation onto 4 terms. In the first term, we are running both indices from 1 to HOMO. In the last term, we are running both indices from LUMO to infinity. I bigger than LUMO, or I can just put infinity. And in the middle, there are two cross terms. When one index runs from 1 to homo, another index goes to infinity. Then first index goes from lumo to infinity, another index goes from 1 to homo. And the content of the objects right after the summation is the same. So let me check if you would approve this little modification of the equation. Please vote by thumbs up if it. Thank you, Lola. Thank you, Umar. Thank you, Hadassah. Thank you, Amara. Thank you, Hanman. Thank you, Adam. Thank you, Amir. Okay. We are progressing really well. Thank you. Now, what the orbitals are, what they are, but what is the difference between elements of density matrix that participate in these four different terms, in these four different segments? On the right part of the slide, I'm making a map of this density matrix as a like square object. And the color code corresponds to range of summation. So the top left quadrant corresponds to summation of both indices from 1 to homo. Lower right quadrant corresponds to summation from lumo to infinity. And the highlights correspond in the equation and in the map correspond to each other. So yellow corresponds from 1 to homo, green corresponds to lumo to infinity. And then there are two cross blocks that have stripes of yellow and green. So let's discuss these objects and give them names. So in case the system is in the ground state, we will have zeros everywhere except the yellow, except the yellow quadrant, which will have ones on the main diagonals, and then the rest will be zeros. Everywhere else, we will have zeros. I believe you approve it. And then we can give little labels and names for these four quadrants. So the yellow quadrant will correspond to valence band, to originally occupied orbitals. It will be the only quadrant that will be non-zero for the ground state. So we are using it for ground state for both indices. And the following notation is my design for the class. It's maybe not common, but I would suggest to call it GG for ground. Then if you look for the lower right quadrant, which in ground state will have only zeros, we can call it EE for excited. And then the cross terms can be labeled as GE for ground excited and EG for excited ground. So ground for this yellow highlighted, excited for green highlighted, and GE, EG for the cross terms. Let's vote if this novelty looks reasonable, or if someone has doubts or criticism or suggestions or questions, please just vote negatively and ask for additional comments. Like, would you approve these new notations, this splitting? Thank you, Hadas. Thank you, Umar. Thank you, Lola. Thank you, Hanman. Thank you, Amara. Thank you, Amir. Thank you, Adam. Okay. Okay, good. So we do have a new protocol to compose density out of orbitals. In case the system is residing in the ground state, this new protocol agrees with standard Kohn-Sham procedure for ground state. And if the system is away from the ground state, we hope that this protocol will be an auxiliary tool, will help us to describe density in the excited state. Okay. So now I am going to refer to the yes, I'm going to refer to the concept of perturbation theory. Again, I will try to show some derivations of TDDFT in what we go through, but here is a little heads up and general context. So, Adam, if you're speaking, I'm not hearing. Just by some reason, your name is highlighted. So if there are comments, please type or speak. If none, I'll continue. So in quantum theory and generally in like natural sciences, there is a concept of so-called perturbation theory, which helps to there are like several brands: time independent, time dependent, and here is the context. The interactions between complicated systems sometimes are not solvable analytically, and even with numerical tools, there are no way to find a solution that is absolutely correct numerical. And there are sets of approximations dealing with assumption that interaction between two classes of systems, and two classes typically are something dramatically different. For the main example I'm looking onto is system of electromagnetic waves and system of like electrons in a molecule. So by assuming that electromagnetic waves have very low intensity, one is looking like they have vanishing intensity, almost no energy that they bring, just little. Then there is a time-dependent perturbation theory that tells how influence of external electromagnetic field modifies the density matrix, modifies the density of a model. And we may start thinking, again, we are yet quite far from exact derivative, but we can think of what would electromagnetic wave do to each of the segments of our density matrix, GG, EE, EG, GE, if it irradiates it for a certain amount of time with certain intensity. And the idea, the philosophy of perturbation theory, that a degree of influence of electromagnetic field onto the certain fragment of the certain part, certain term in the overall density is proportional to the transition dipole and intensity of electric field. And this idea, again, we are yet far from rigorosity. It's just general idea, is summarized in this equation. So if the electric field is vanishing, we assume that ground state is not changed. So the contribution of the ground state density stays the same, although one should withdraw something. The contributions to EG and GE are proportional to the first power of this transition dipole times intensity of the electric field. And the contribution to excited state density, rho EE, is proportional to transition dipole times intensity, the strength of electric field squared. So in case electric field is truly small, if it is like, if the product mu times E is less than 1 in certain units. So let's just do a very, it's like not serious science. It's just an example for not kindergarten, but just closer to joke rather than derivation. But if mu E is 0.1, then mu E squared will be 0.01. And 0.01 is much smaller than 1, right? Therefore, second order correction can be neglected, right? So in the lowest order correction, the influence of oscillating electric field will perturb only diagonal terms in the density matrix. So these diagonal terms in the density matrix that we agreed to discuss today become non-zero if our system of our electronic system does experience transition, optically induced transition from ground to excited state, or backwards from excited to ground, right? So please vote if you are okay with this statement, if this naming. So these diagonal terms are non-zero if system is experiencing, thank you, Lola, transitions. If you're not happy, just vote against. Thank you, Adam. Thank you, Umar. Thank you, Amara. Thank you, Amir. Thank you, Hadassah. Okay. Therefore, these terms, rho EG and rho GE, are referred to as transition density. So it is contribution to total density that is activated if system is in the active transfer, if it is in the transition between ground and excited. And in a narrow sense, the time-dependent density functional theory, in a very narrow sense, you will not see it if you look into Wikipedia, is a theory of finding transition density as function of frequency of exciting electromagnetic field. So in the community of time-dependent density functional theory, the EG and GE are referred as symbols X capital and Y capital. And the TDDFT takes as an input frequency of light, and as an input finds X of omega and Y of omega. So it is like oversimplified summary of the time-dependent density functional theory. Let's see. Okay, I believe it is, even if we didn't approach the end of slides, it's I think it is enough new information. So I suggest we just finish the meeting at this point and continue academic part of the course next Monday. So I look forward seeing you all in the lab tomorrow. And meeting is dismissed. Everyone is welcome to disconnect, but I'll stay here. If you have questions, please stay connected and ask any questions. Okay. Thank you.
Yeah, Dr. Kling, I had a question.
Oh, yes, please.
All right, so if I'm running something on nurse and I want to stop it, what command would I use?
S cancel.
Okay,
Yes,
and
cancel space and then the index of the job ID. When you type S batch, it gives you index of a job, right?
yes.
And if you run it by error, just type S cancel space and then the index. But note, the account is getting charged for numerical resources, and the charge is happening at the time of a job submission. So if you stop running, the resources are not returned to account. So if it is not completely wrong job, if you are thinking only about saving resources, do not stop. Let it go.
Okay, yeah, it was I found out I couldn't do Emacs with an RSC, so I accidentally did an Emacs window I couldn't close. So yeah, all right, thank you.
Yeah, thank you. Hello, how are you?
I wanted to talk about forms you suggest that I use for the project.
Would you please enable camera? It will help me to recognize, just to speak a little better. And I'm going to stop sharing the screen. And let me stop